Wow, so you've reached a milestone in Math SL. Today's your first day of calculus problems. Page one. Um, on page 345, we talk about why we need limits. What are limits? Well, let's talk about why they're useful here. Sometimes we have a function which cannot be evaluated at a certain point. For example, this function here. As we learned before with asymptotes, when you have a 0 in the denominator, like here if x equals 0, then that would be 0 in the denominator. That would be a problem. There would not be a number as an output for that, and you would get an asymptote, right? Um, but the thing is, it's like just because you can't evaluate the value of f of x at the point x equals 0 doesn't mean you can't notice a trend as to where it would be if it did exist, okay? Because like if you look at all the numbers that f of x takes on to the left of x equals 0 and to the right of x equals 0, you might notice that if f of x did exist at that point, then it would have a finite value. Okay, and that makes no sense right now, but when we do the exercise, you'll see. So when we substitute x equals 0 into this expression, what happens? We end up with 0 on the bottom, of course, and what do we end up on top? Also 0. Okay, 0 over 0, which has no meaning in math. Okay, moving on. But we can calculate its value at any other point besides x equals 0. So evaluate f of x for these values of x. Okay, so just to make things easy for you, I did a little bit of algebra here, or the book did anyway, and it factored out an x from the top. And so you can see that there's an x on the bottom, x on the top, right? So that makes it a little bit easier to calculate this value, right? So like, for example, if you put -1 in for x, for example, you're going to get 5 minus 1 there, which would be 4, and then you would have times -1, which would be -4, and then you divide by -1, and that would make it just 4. Okay, so the value here would be 4. And as you'll notice later, these two x's kind of cancel each other out, right? So for any other value besides x equals 0, they like one undoes the other. So really the only thing you have to do is you have to do 5 plus x, and that's it. So let's do 5 plus x here. We'll get 4.9, and here we'll get 4.999. Okay, and what about here? We'll get 5.001, and here we'll get 5.1, and here we'll get 6. Okay, and we can't put 0 in, of course. If we put 0 in, then the denominator is 0, the numerator is 0, and doesn't exist. So I put the x there. Okay, so do you notice a trend here? I mean, if you compare this value to this value to this value, you can see that each step we take, we are getting closer and closer to the number 5.0, right? And if we go from the right to left, 6, 5.1, 5.001, you can see that with each step we take, we get closer and closer to 5.0 again. Okay? So, even though when you evaluate that function at x equals 0, you get this meaningless thing, the trend is for that point to evaluate to 5. Because immediately to the left, it looks like it's approaching 5. Immediately to the right, it looks like it's approaching 5. So isn't that kind of weird? Okay, so limits evaluate these trends of neighboring points, even if there's a certain point where you can't evaluate the actual value. So what do you notice about the two middle values, which are close to the 0? What numbers are they close to? They're close to 5, right? Okay, so actually f of x approaches 5. You have just shown the purpose of a limit, although the value f of 0 does not exist due to the division by 0. Using the smooth trend of values of f of x as x gets closer to 0, we can see what f of 0 might be if it existed. Okay? So it is read as the limit of f of x as x approaches 0. That's how you read that there. Okay? And the limit is, or where does it approach? It approaches 5. So the answer here is 5. Notice in this case that f of x approaches the same value approaching from the left or from the right. So like you can see that like from the left it's 4.999, from the right it's 5.001, but from both sides it's approaching the value 5.000, right? That's not always the case, but it is in this case. Okay. Number one, we're going to do some limits here, and in most cases, all you need to do is say, hey, well, I could just put in the value. Like if I put a 3 in for x, I would get 3 plus 4, and that would be 7, right? And there's not really anything wrong with doing that. Obviously, if you put in 2.9999, you're going to get something very close to 7. If you put 3.0001, you're going to get something close to 7 also, right? The only problem that you have is if you have a case like this where, it gets to the critical point and it explodes, becomes infinity or 0 over 0 or something illegal, okay? But if it doesn't, then it's pretty easy. You just plug in the number. So when as x approaches 4, then I'm going to get 3 times 4, which is 12, minus 1, which is 11. Okay? If I put in 3.9999, I would get something very close to 11. If I put 4.00001, I would get something very close to 11 also. Okay? For this next one, if I put 0 in for h, then I would get 0 times 1 minus 0, which is just 0, right? And if I put something very close to 0, like 0.00001, I would also get something very close to 0. So the limit is 0. What about here? The limit as x approaches 0 of 5. Well, 5 does not change, depending on the value of x. X can be anything. 5 is still going to be 5. So this is kind of a silly question. And then they generalize. If you have c, which is a constant, not related, it doesn't depend on x, doesn't matter what x's value is, c is always going to be c. Okay, moving on. Evaluate the following limits. The limit as x approaches 0 of this expression. This is similar to the expression above, right? So we could rewrite this as, like they did, we factor out the x, and we get x minus 3 here, and we get x here, okay? So if we put in 0, we're going to get an illegal value. We'll get 0 over 0. But if we put a very small number, then you can see that this and this cancel out, right? So really what matters is x equals 3. And if we put a very small number like 0.0001, we'll get like negative 2.9999. Or if we put something very small like negative 0.0001, then we get negative 3.001. So you can see that we're approaching a common number from the left and the right. So basically that number is negative 3, right? Okay. What about this one here? Same thing. We can factor out the x. Okay, so we're going to have limit as x approaches 0 of x to x minus 1, and we have x on the bottom, right? And then, so you can see that like under normal conditions, these x's will cancel out. The only time you can't cancel it out is if x equals 0, okay? And then like, oops, there should be an arrow there. So if we put 0 in for 2x minus 1, we're going to get negative 1, right? And even if we put something very small like 0.0001, we're still going to get something very close to negative 1. So the limit here is negative 1, okay? What about this next one? So here we're going to say limit as h approaches 0 is h times 3h minus 4 divided by h. And again, we have this condition where the h's cancel out unless h is 0. Okay, so when h becomes 0, the 3h minus 4 becomes negative 4. And even if we put something very small like 0.0001, we're still going to get, negative 0.3999 and something very close to negative 4. From the left side, from the right side, we're always going to get something close to negative 4. Okay. Moving on to G. The limit as x approaches 1 of x squared minus x divided by x minus 1. Again, we can factor out an x here. And ironically, it's not the x which helps. Do you see what happened here? Now, what cancels out is this and this. And so when x equals 1, then the denominator becomes 0. But we're not going to make x equal to 1. We're going to make x approach 1. Okay? So now we can see that this is going to be if we put something like 1.0001, then out is going to come 1.001. And if we put something like 0.9999, then out will come 0.9999. Okay? So basically what we're approaching here is the value 1. Okay? Um, what about I? So we got x squared minus x minus 6 and x minus 3 on the bottom. And just like before, we need to factor something out so that the top and bottom kind of cancel out. Okay? And hint, hint, one of the factors is going to be x minus 3, right? Because the bottom is x minus 3. Okay, so we'll factor out x minus 3. It's going to be something like plus 2, I think. Plus 2. So let's check if that's right. Negative 3 times plus 2 is negative 6. Yes. Negative 3x plus 2x is negative x. Yes. So that's the correct factoring. Okay. And then we can see that these two would cancel out except when x equals 3. Okay. We can't cancel out when x equals 3. So basically we can say that the limit as x approaches 3 is going to be 5. Because if we put 3 in for here, then we're going to get 5, right? If we put 2.999 in or 3.10001 in, we're going to get something close to 5. Okay? So basically, that's our limit there. That's our limit there.